So how do we put this knowledge to work? How do we put this PN junction trivalent, pentavalent um, impurity information to work? Well, if you take a block of silicone and dope half of it with the trivalent impurity and the other half with a pentavalent impurity, we form a boundary called a PN junction. And it's formed between the resulting P-type and N-type portions of the semiconduction diode. So initially, there is no movement of electrons or current through a diode when it's at equilibrium. The primary usefulness then of a diode is its ability to allow current in only one direction and to prevent current in the other direction. This is something we call setting up the bias. In electronics, bias refers to the use of a DC voltage to establish certain operating conditions for an electronic device. There are two practical bias conditions for a diode: forward bias and reverse bias. Either of these conditions is created by application of a sufficient external operating condition, okay, a sufficient external voltage of the proper polarity across the PN junction. So we have to apply some sort of excitation, something external, to start making things happen, for things to start cooking on either side of that junction. So a diode consists of an N region and a P region separated by a PN junction. So if you take a look at the diagram below, you can see diagrammatically we have the P region on the left, the N region on the right, and where the two are joined we call the junction, or the PN junction. The N region has many conduction electrons. The P region has many holes. So you can see there are lots of holes on the left hand side, there are lots of electrons on the right hand side. With no external voltage, the conduction electrons in the N region are randomly drifting in all directions. At the instant of junction formation, some of the electrons near the junction drift across into the P region and recombine with holes near the junction. So we can see that then in the diagram. So lots of randomness going on the left side here. On the right side here, we see holes trying to be filled by electrons and electrons trying to fill holes. Okay, so it's a back and forth action. You see across the region electrons and holes, holes and electrons. So for every electron that diffuses across the junction and combines with a hole, a positive charge is left in the N region and a negative charge is created in the P region, forming a barrier potential. This action continues until the voltage of the barrier repels further diffusion. It's kind of like water reaching its own level. Okay, so this is what's going on in the junction here, or on either side of the junction. So at the instant of junction formation, some of the electrons near the junction drift across to the P region and recombine with the holes near the junction. For every electron that crosses the junction and recombines with a hole, a pentavalent atom is left with a net positive charge in the N region near the junction, making it a positive ion. Also, when the electron recombines with the hole in the P region, a trivalent atom acquires a net negative charge, making it a negative ion. As a result of this recombination process, a large number of positive and negative ions builds up near the p-n junction. As this buildup occurs, the electrons in the n region must overcome both the attraction of the positive ions and the repulsion of the negative ions in order to migrate into the n or the p region. Thus, as the ion layers build up, the area on both sides of the junction becomes essentially depleted of any conduction electrons or holes and is known as the depletion region. This condition is illustrated when an equilibrium condition is reached. The depletion region has widened to a point where no more electrons can cross the p-n junction. Okay, so we see this action here on the right hand side, that the holes in the electrons are forming into the barrier potential and creating the depletion region. The existence of the positive and negative ions on opposite sides of the p-n junction creates a barrier potential across the depletion region. The barrier potential, V sub B, is the amount of voltage required to move electrons through the depletion region. At 25 degrees Celsius, which is a little more than 70 degrees Fahrenheit, it is approximately 7/10 of a volt for silicon, 3/10 of a volt for germanium. These two values are very important because these are the values that you will use in your analysis and the values that you will use in setting up a bias in different types of materials, whether it's silicone or germanium, to make it go into conduction. As the junction temperature increases, the barrier potential decreases, and vice versa. So, biasing a diode. Forward bias is a condition that permits current through a diode. The diagram shows a DC voltage connected in a direction to forward bias the p-n junction. Notice that the negative terminal of the V bias source is connected to the N region, and the positive terminal is connected to the P region. So you can see that here. We put a little bit of a load on there, a little load resistor, positive on the P, negative on the N. A discussion of the basic operation of forward bias follows. The negative terminal of the bias voltage source pushes the conduction band electrons in the N region toward the p-n junction, while the positive terminal pushes the holes in the P region also toward the p-n junction. If you go back to chapter 2 of the text, you'll recall that like charges repel each other. Okay, that's fundamental. When it overcomes the barrier potential VB, the external voltage source provides the N region electrons with enough energy to penetrate the depletion region and move through the junction. When they combine with the P region holes, as the electrons leave the N region, more flow in from the negative terminal of the bias voltage source. Thus, current through the N region is formed by the movement of conduction electrons, the majority carriers, toward the p-n junction. Once the conduction electrons enter the P region and combine with holes, they become valence electrons. Then they move as valence electrons from hole to hole toward the positive connection of the bias voltage source. The movement of these valence electrons is the same as the movement in the opposite direction. Thus, current in the P region is formed by the movement of holes, the majority carriers, toward the p-n junction. Figure 16.2 then in your text illustrates the current in a forward biased diode. So you can see here The depiction then, current in the forward bias diode. It looks like a very rushed operation going on here as these electrons in these holes are scrambling to um, to hook up with each other. Electrons filling holes, holes taking on electrons. The effect of the barrier potential in the depletion region then is to oppose the forward bias. This is because the negative ions near the junction of the P region tend to prevent electrons from moving through the junction into the P region. You can think of the barrier potential effect as simulating a small battery connected in the direction to oppose the forward bias voltage. Okay, the resistances R sub P and R sub N represent the dynamic resistances of the P and N material. So you can see here how they've set this up um, with the idea then of these resistance P and N with a source in the potential in the depletion region. The external bias voltage must overcome the effect of the barrier potential before the diode conducts. Conduction occurs at approximately 7/10 of a volt for silicon. Remember, it's 3/10 for germanium. Once the diode is conducting in the forward direction, the voltage across it remains at approximately the barrier potential and changes very little with changes in the forward current I sub F. Okay, so this just gives you an idea of what's going on, if you could think of it in terms of a source and some resistances. For a reverse bias, the condition that prevents current flow through the diode, if we look in your text on page 730, it shows a DC voltage source connected to reverse bias the diode. Notice that the negative terminal of the V bias source is connected to the P region and the positive terminal is connected to the N region. A discussion of the basic operation of the reverse bias then follows. The negative terminal of the bias voltage source attracts holes in the P region away from the PN junction, while the positive terminal also attracts electrons away from the PN junction. As electrons and holes move away from the PN junction, the depletion region widens. So under a forward bias, the depletion region narrows, and it makes it easier for the electrons in the holes to pass through the barrier. When you reverse bias, or in essence putting it in a shut-off mode, you're opening that depletion region. It is very difficult then for the flow to occur. A discussion of the basic operation then shows that the initial flow of majority carriers away from the PN junction is called transient current and lasts only for a short time upon application of the reverse bias. The depletion region widens until the potential difference across it equals the external bias voltage. At this point, the holes and electrons stop moving away from the PN junction. The majority current ceases. Okay, so that's how we control the current in a diode, by narrowing and opening the depletion region by putting a potential, forward and reverse potential, on the diode so that it is actually exciting the positive and negative, or the electrons and holes in opposite. So if you take a look at the diagram here, you can see here what's going on diagrammatically. If you put some current and voltage meters, you can see the voltage meter forward, current forward, with no source on here. Everything is zeroed out. So now if we start to add a forward bias in here, you can see that 7/10 of a volt silicone. We can see the potential starting to grow. We see the current starting to build up a little bit, and we have lots of bias voltage then from the source at the input. The forward bias then reaches and remains at approximately 7/10 of a volt, so we can see that across the diode itself, taking a measurement. Forward current then continues to increase then as the bias voltage increases. So we reach that 7/10. If we start to go over it, we force the diode into conduction heavier, and when we do, you can see that the current increases dramatically. We can see here that across the source where the bias is, we have a large um, bias voltage applied. So when the diode is reverse biased, the depletion region effectively acts as an insulator between the layers of oppositely charged ions, forming an effective capacitance. Since the depletion region widens with the increased reverse bias voltage, the capacitance decreases and vice versa. The internal capacitance is called the depletion region capacitance. As you've learned, majority current quickly becomes zero when the reverse bias is applied. There is, however, a very small current produced by minority carriers during the reverse bias. This current is typically in the microamp or nanoamp region, so 10 to the minus 6, 10 to the minus ninth amounts of current. A relatively small number of thermally produced electron hole pairs exist in the depletion region. Under the influence of an external voltage, some electrons manage to diffuse across the p-n junction before recombination. This process establishes a small minority carrier current throughout the material. The reverse current is dependent primarily on the junction temperature and not on the amount of reverse bias voltage. A temperature increase causes an increase in reverse current. Okay, so we can see here diagrammatically reverse bias connection. There's a transient current. As the depletion region widens, the majority carriers cease when the barrier potential equals the bias voltage. Okay. There is another condition called reverse breakdown. If the external reverse bias voltage is increased to a large enough value, reverse breakdown occurs. The following describes: assume that one minority conduction band electron acquires enough energy from the external source to accelerate toward the positive end of the diode. During its travel, it collides with an atom and imparts enough energy to knock a valence electron into the conduction band. There are now two conduction band electrons. Each will collide with an atom, knocking two more valence electrons into the conduction band. There are now four conduction electrons, which in turn knock four more into the conduction band. This rapid multiplication of conduction band electrons, known as the avalanche effect, results in a rapid buildup of reverse current. Most diodes normally do not operate in the reverse breakdown and can be damaged if they are. However, there is a particular type of diode we will learn about called the Zener Diode. It's specifically designed for reverse breakdown operation. So when we come back, we'll take a look at diode characteristics.